So let's say, oh boy, let's just say I tell you that X, oops, I got the wrong color out here. And do you know if they're going to be X-axis or Y-axis, or do you think that even matters?
It's probably going to be X-axis.
Okay, so let's say it's Y equals 1/2 X, and we're going to go from 0 to 4, and the cross sections, we'll just keep it kind of simple to start here, are circles with diameter between the x-axis and this curve. So you might start by graphing 1/2 X. You get something that looks like that. 0 to 4, kind of this triangular shape here. And then you would maybe want to, and it's nice when I've got another color here. They're circles. This is the diameter, so it's kind of like this is the circle and this is the other circle there, like that. So in your problem here, you've got to say, okay, well, this up here is 1/2 X, but is that what I really want? No, the diameter is 1/2 X. The radius is this divided by 2, 1/4 X. Okay, and then you set up your integral. Your integral is from 0 to 4 pi r squared dx, but your r is this function here. Something like that. Is that kind of what you had in mind, this type of problem here?
Yeah.
Okay, so how would this problem change? Let's say it's the exact same thing. It's y equals 1/2 X, 0 to 4. But now we also add in the line y equals 2. Okay, and it's the region between them. So here's y equals 2. Here's 1/2 X. It's this region now. Let's say we wanted squares with side length. And I don't know how it's going to be worded, but we'll say that region between here. How would that change this problem?
Well, the side length is going to be equal to pretty much the space between 2 and 1/2 X.
That's right. And so what would S be, in terms of meaning that side length? What could you come up with an equation for it?
I'd say 2 minus 1/2 X.
Yes, that's perfect. So that represents this right here. And if you're ever unsure, you can try it at its two endpoints, when x equals 0 and x equals 4, and it should give you 2 and then 0 if it works, and it does. Okay, so the volume of these cross sections is always the integral from a to b, and then you've got some sort of area function dx. So in this case, your area function is squares. Right? So your squares are s squared. So it would be 2 minus 1/2 x squared. How would you work this integral out here? So it's from 0 to 4, 2 minus 1/2 x squared dx. What would you do to work this out?
Well, I'd probably actually simplify it first so that you don't have the squared brackets and you have a full trinomial.
Yes, I agree, and that will help here. So the other types of geometries that you could be given, and let's make up another problem here. Let's say it's y equals e to the x, and let's go with y equals natural log of 2. Let me actually graph that to make sure it's reasonable. 2. That's not reasonable. Let's go. Actually, let me just change this to no, I'm trying to think of some other functions that might be more interesting. Let's not go with that. Let's go with y equals the square root of x, and let's go with y equals 3. Okay, so we want the region between them, but this time the cross sections will be, and this is where I guess I want to ask, I want to do something more difficult, but like if I say the right triangles, but it represents the they're isosceles right triangles, but it represents the hypotenuse. Would that be, would that be too difficult? I guess is the question. Is like, you can see the square root of x looks like that. It goes out to 1, 2, 3, 4, 5, 6, 7, 8, 9, 3. So it's this region right here, but this time this part in here is actually the hypotenuse of the right triangle. So it's like the right triangle has a right angle there. Do you think that would be too much for this class? Or is that reasonable to do?
Honestly, I'm not entirely sure. I think it's possible, so I can see how it works.
Because if it's just the side, the area of a triangle is base times height 1/2. But when you do it this way, you have to like back it off and figure like, well, how do I go from the hypotenuse? Okay, so in this case, the hypotenuse is 3 minus the square root of x. How do I find the side length of an isosceles right triangle? So to do that, the sides are actually the same.
Mhm.
And this is actually a 45, 45, 90 triangle. That's why I'm asking, like maybe it's, too much incorporation of other stuff, but s squared plus s squared equals 3 minus square root of x squared. 2s squared equals 3 minus square root of x squared. But then you divide by 2 and take a square root. So your side length is whatever it is, but you actually just want s squared because the area of the triangle is 1/2 base times height, and your bases are the same, so it's really 1/2 s squared.
Mhm.
So your s squared is 3 minus square root of x squared over 2. So your problem would be 1/2 3 minus square root of x squared all over 2. And
Okay.
so it looks maybe more challenging it is, but you would do the same thing actually as in the last problem. You would just expand that binomial, find the antiderivative, and evaluate the endpoints.
Okay.
I grabbed 2 textbooks and neither of them are quickly allowing me to find any cross-section problems. I apologize. I was really remember seeing some of these. The textbooks are usually faster than going out to the internet, but not in this case. Did we cover, is there any cross sections you would like us to cover in more detail?
I guess like one problem I have seen before is like with square cross sections, but it uses the diagonal instead of the side.
Great. Yeah, that's another variation. So here, let me grab a problem here. Let's say it's x squared plus y squared equals 1. And like you said, the cross sections are diagonals. Okay, so in this case, this is a circle, and I'll just make it a little bigger to be able to like more easily like work with here. But let's go like this again, not to scale. There's your nice circle there. I actually prefer to look at just the top half of this, which is just a minor modification of the problem, but I think sometimes there's too much going on there. So the top half is y equals square root 1 minus x squared. And if you care, the bottom is just the negative of that. It's the square root of 1 minus x squared for the bottom. So the like you said, the diagonal is here. This is the diagonal. Well, if we call this is half the diagonal. So it's just like an extra step, but I mean, I find it's sometimes a little more useful. So if I draw a square, and I put this red here to indicate that it's the diagonal. The diagonal is 2 of these square root 1 minus x squareds, because this is half the diagonal. If you did top minus bottom, you would get square root of something minus the square root of the same thing. And that's why there's 2 of them. Okay. A square, actually this, we actually just did this. The square is it's a 45, 45, 90 triangle. And if you recall, the reference is that x root 2. And what that means is to go backwards to a side length. And the reason we want the side length is we want the area, is if this is the hypotenuse, it's x divided by the square root of 2.
Mhm.
So basically the side length here, s equals 2 square root 1 minus x squared, which you divide it by the square root of 2.
Okay.
And it looks bad, but because you're finding the area of a square, which is s squared, you end up squaring what you were given here, which takes care of a lot of the stuff here that we found very unpleasant. So this becomes 2 minus 2x squared. And that's what you're going to integrate. You always integrate this area function here. And what I've been trying to show you here is like what I would actually do is I would maybe draw it, but I would show it in the cross section thing that they're trying to emphasize here.
Mhm.
I actually found some more problems in the book if you want, or we can just move on to some other stuff.
I wouldn't mind seeing what's in the book, at least 1 or 2.
Okay, let's do it. So the next one here looks kind of interesting. Is it says it's y equals this 2 square root sine x, and it goes from 0 to pi. And this time it says that the cross sections are right triangles. I'm sorry, the leg of an isosceles right triangle. Okay. So I'll graph this for you because I think that is only fair to kind of give you an idea what this looks like. From 0 to pi, it looks like this. Okay. So why don't you take 2 to 3 minutes here and see if you can work this one out, and then I'll jump in and show you the solution. But you do have enough here to actually do this. Does that work for you?
Yep.
Great. I'll stand by. I'm gonna just start working this out. You're welcome to interrupt me if you've got questions or just keep working. How does your answer stack up to mine?
I did basic addition wrong, but other than that, it matches.
Okay. Well, hopefully you got a positive number, and if you didn't, know to check yourself because obviously it's positive. If you got your antiderivative wrong, that could affect some sign, things like that. Your instructor has an obligation to give you reasonable functions to integrate because that's not the part of the problem there that they're trying to emphasize. So just keep that in mind. Okay, let's do one more. You said you mentioned another one. Let's get another, I don't know, exam. I would think it's exam quality. Y equals x squared. Y equals 2 minus x squared. They actually tell you that it goes from -1 to 1, but you could actually solve for that by setting them equal and figuring that out yourself if you really had to. And this time the cross sections are diameters of a circle. Would you like a graph of this, or would you like to try and do it on your own?
I'd like to try and do it on my own.
All right, take another 2-3 minutes and see what you come up with.
Okay.
right, so I'm gonna just jump in here and work this out. The diameter in this case is the difference, the top minus the bottom, which looks like it will end up being 2 minus 2x squared when you subtract them. And since you really want the radius is going to be 1/2 of that. Your integral goes from -1 to 1 pi, your radius function squared dx. Okay, so that's 1 minus 2x squared plus x to the 4th. Then your antiderivative. Fortunately, this one does have 2 bounds to evaluate. 1 minus 2/3 plus 1/5. So one of the reasons I do it this way is that you can actually combine things that go together, like the 2 goes together, the 2/3 go together, and then the 1/5, and then I would make a common denominator. I wouldn't necessarily do it from the beginning because I don't even know what it would be, but it's 15 in this case. So 30 minus 20 plus 6. So maybe 16/15 pi. Possible there's a mistake there in evaluating, but should look something like that when you're all done. Main thing is, can you set it up? Can you set it up? Can you find the right geometry? Can you then evaluate the integral and evaluate the endpoints?
Mhm.
Okay, what topic should we look at next?
Mhm.
You sent a great long list yesterday. I'm just going to pull that up in case you want me to refer to it.
I suppose arc length.
Arc length. All right, good choice. Okay, so this does have a formula, and I'm going to write it out. I don't want to mess it up, so I'm going to go grab it from a reference here. The arc length is, and it could be done in either X or Y. I'm not sure how much like your instructor is emphasizing that, but the resource that I like to use, it shows it both ways. It says, okay, if you're doing it with respect to X, it's this one. And if it's respect to the Y, it's another one. All right. So anything, is that okay? Is that formula something that you've seen before?
Yep.
Okay. Let me find some problems that are reasonable. So a lot of these end up being calculator problems, but let's see if I can find one that's not too bad. All right, so here's one you probably haven't seen before because it's in a textbook. They say y equals 4/3 square root of 2 x to the 3/2 minus 1. Okay, so something like this would be given, and it tells you it's from 0 less than or equal to x less than or equal to 1. So that gives you the bounds of your integral.
Mhm.
The first thing that you should do immediately is take a derivative. If you haven't done one of these in a while, that's where it's like, what do I do? So power rule here, 3/2 times 4/3 square root of 2 x to the 1/2. That goes away. So you end up getting 2 root 2 x to the 1/2, and then you square it. So you get y prime squared, square both sides. So you get 4 times 2, 8x, like that. And your L is the integral from 0 to 1, square root 1 plus 8x, whatever. And that's why I like to do it here. I don't like to square it inside there because that could get messy.
Yeah.
So this right here is known. It's a U substitution if you want. There are kind of like some antiderivative reference sheets have this as a formula, but we'll do it as a U sub. So the U sub here, you let U equal 1 plus 8x, du equals 8 dx. U of 0 is 1, putting 0 in for x. U of 1 is 9. So it becomes the new integral for the length of this, it becomes the integral 1 to 9, square root of u, and then dx is du over 8. Just a slight rewrite here. 1/8 integral 1 to 9 u to the 1/2 du. And now it's just a basic, sorry, I jumped forward too much. It's just a basic antiderivative u to the 3/2, 2/3 out in front, 1/8 here evaluated from 1 to 9. And so we've got that cancels that. So you get 1/12 times 9. Now, instead of writing 9, the more you do these, the more you realize I really just need it as 3 squared to be able to analyze this. Minus 1 to the 3/2 because 1 to any power is 1. But 3 squared to the 3/2 power, 2 times 3/2, exponent to an exponent, you multiply, the 2's cancel, you get 3 cubed. So you get 27 minus 1, 26 divided by 12 ends up being 13 over 6. The truth, though, is that almost none of these work out nicely. Almost none.
Yay.
And I'm sorry. So they tend to only, so you probably only get one on the exam because there's just not that many that they can do here. So this is a common one. You might see, trying to find one here. That one doesn't work nicely. All right, so this is kind of their vanilla one that you would probably see, like y equals secant. Nope, that won't work. Sorry. Y equals tangent x from minus pi over 3 to 0. So the first thing you do here is you take your derivative. What do you recall your derivative of tangent?
Secant squared.
Secant squared x, great. And then you square both sides. So you get secant to the 4th x. This one doesn't work. Sorry, I messed up. So this ends up being the integral from minus pi over 3 to 0, square root 1 plus secant to the 4th x dx. And I was trying to find something that would work out nicely. This one does not. All right, so let me give you one that actually does, I think. Gosh, it's like they almost have to be all of the same type to work out nicely. We do these. So. But they really don't emphasize this at all. This book. Okay, so let's say y equals cosine x, and we want to go from 0 to pi. I think this one does work. So what would the derivative of cosine be?
Negative sine.
Negative sine. This isn't going to work. I'm sorry. This one doesn't work either. I'm so sorry. Yeah, this is no good. All right, so let me I guess, okay, so let me try one here. So the problem is when you square something, that it has to work out nicely. So the derivative of this is 1/2 x to the minus 1/2 power. This one also doesn't work. It's got to be an x to the 3/2. Oh. Would you like us to move on to another topic, or?
We can move on.
Okay. What else would you like to have some look at on these? I see work problems. I see surface area. Maybe we haven't done any of those, but that's just a setup.
Do surface area real quick.
Okay. All right, so surface area. So let's go with, there's this Gabriel's horn problem that's kind of interesting. Surface area. $389. Oh, this one doesn't give the formula. Okay, let me go grab the formula for this. All right, so the surface area, again, it's kind of like there's one with respect to x, one with respect to y, but most of the time you're going to do it with respect to x. So it's 2 pi y ds, and ds is actually the same as the arc length, 1 plus dy dx squared. Okay, so for, and I got to give you a problem here. So y equals, so let's just do this one. So they have to give you y, like let's say they give you y equals 1 over x. And you have to do the same thing we did in the previous problem. You have to find the derivative, minus 1 over x squared. Then you have to square it. So your instructor is like grading on your ability to like follow this sequence. So that ends up being y prime squared. Y prime is the same as dy dx as 1 over x to the 4th. And as I mentioned, these are setup problems. So you're setting up this integral 2 pi times y. Y is really your function of x. I think that's sometimes unclear. This means y of x, or whatever y equals. In this case, it's 1 over x, and it's the square root of 1 plus 1 over x to the 4th dx. And then I have to tell you it goes from, like, let's say 0 to 1, maybe.
Mm-hmm.
And because you're setting it up, they're not asking you to they're just asking you to follow these steps. You don't have to make any decision about how to actually do it.
Yeah.
Like that. So let's have you try one here. Let's say, all right, so let's say I give you, again, you could just set this up. Let's say it's y equals 3x minus x squared. And we're going from 0 less than or equal to x less than or equal to 3. So why don't you give that one a try and see if you can set up. Do you need me to pull up the surface area integral? Do you have this down?
I have it.
You got it. Okay. All right. So give this one a try.
I do think I'm done.
All right. So the setup here is y prime equals 3 minus 2x. Then you square it. So you should square it 9 minus 12x plus 4x squared. And you should simplify it. So your integral is 0 to 3, 2 pi, parentheses 3x minus x squared. Times the square root of 1 plus 9 minus 12x plus 4x squared.
Yep.
Okay. And then dx, don't forget about that. Any chance you'll get one around the y-axis, or does that seem like out of scope?
I'm thinking probably not.
Okay. So the formulas for arc length and surface area, they're really similar. Arc length is, and sometimes just simplified as the square root of 1 plus dy dx squared. And for surface area, it's the integral 2 pi y square root 1 plus dy dx squared dx. You can see they're very much the same.
Mm-hmm.
All right, we got time for like maybe one more topic and a problem or two. So give me some direction here. Anything stand out to you that you would like to work on?
Maybe rate of change.
Okay. So rate of change here. Quickly see if I got any problems. That probably the next chapter. Okay, so let's say the amount coming in is I don't know. These are calculator problems or not? Probably.
Probably calculated.
Okay. let's go, let me graph something real quick to find something reasonable. Why can't I? There it is. Four x minus x squared from 0 to 4, and then out is sine squared x. Okay, and so the question would be, and let's say you started with, this is also from 0 to 4, and let's say you started with 100 gallons. They would ask you to set up the integral for like the amount at time t, or the the in minus out. So it's always the whatever you're starting with plus the in minus the out. But these are both rates that I gave you. Like this up here is a rate and this up here is a rate, which means you can't just use them directly. You have to integrate them from whatever bound. So it's like 100 plus the integral 0 to, actually, let's go x there, 0 to x. And then it was like 4t minus t squared dt minus the integral from 0 to x sine squared t dt.
Mhm.
And I could ask you questions like, well, what is a of 2, kind of thing like that. Now if you graph them together, which you would have because you would have a calculator here, let me see if I can get the n minus out. Or actually, let me just graph the whole thing. 100 plus, I'm sorry, not just the rates, the n minus out. So it'd be like 4x minus x squared. And it's kind of a funky graph. Let me grab it here, there. Let me just restrict this to 0, 4. So I can get those points. Okay. So this is a graph of the rate versus time. Okay.
Mhm.
And I could ask you where the, I could ask you from the graph here to tell me something like, well, what's going on at this point here? Like, what does this point mean here? Because up until there, the area above is above, so it's positive. But then right before 4, it goes negative. So is that a min or is it a max? And we're talking about the rate. So the rate is, and that's your derivative rules. It's like if you go from plus to minus, that's a max. If you go from minus to plus, that's a min. And since it's above, because it's a rate, it's a derivative. Okay, it's considered positive up here and then negative down here. So this point is actually a max. So if I wanted to know what that like actual max is, you would have to integrate from 0 to the 3.8333.
Mhm.
And then maybe a final question here. It would say something like the like assume that this keeps going. You would somehow be told like this keeps going, and it would be like, well, when is it 0? Okay, when does the amount equal 0? Because it's 100 plus the two integrals. The integrals from 0 to x, 4t minus t squared dt minus integral 0 to x sine squared t dt. Because eventually this area below will equal this area above and the 100.
Yeah.
And they could ask you to like either set it up like this, but not evaluate, or through some, well, this one would be tough because you couldn't find the answer to that, but you could maybe estimate it, roughly. Like maybe the answer would be like, well, within like 6 to 7 hours or something like that, 7 to 8. but that would be an example of that.
Mhm.
All right. Well, I hope this helped. You're probably more prepared than you think. At least that's what I remember when I was a student. And if you have time, maybe review the exercises again that we've done. But if not, you've done all you can, and just give it the best shot you can tomorrow.
Thank you.
You're welcome. Hope you have a great night, and I'll send you the notes here shortly.
Mhm.
Thank you. Bye now.
Bye.